Hello ladies and gentlemen, in this video we are going to solve an easy problem called invert binary tree. So invert binary tree, so let's take a look at the input. So you're getting 4, left 2 and right 7. So in the invert version you swap the right and left child of the tree. So 2 and 7 end up here, and over here you can see the 1 comes over here, 9 goes over there, and 6 basically what's happening is that 2, so let's think about it now. So you got 4, just copy and paste it here. I'll try my best here. Alright, so here we go. So we got this tree, right? So the result is basically we are changing the right side of the root would be on the its left, and the left would be on its right. So basically, if you just say root dot left is equal to its root dot right, and then root dot right is equal to its root dot left, this would basically solve the problem. Because alright, so first time we do that is basically what's gonna do. Our root is 4, right? Just remember our root is 4. So if we run the first line of code and the second line of code, when we run the first line of code, root dot left, which is this left side, it's gonna take the entire right. So it's the right is 7, 6 and 9, right? So I'm just gonna copy 7, 6 and 9. Okay, so we just copy and then delete this part. Alright, gotta delete this. Alright, so it's gonna take, so as you see that the right child of 4 is 7, 6, 9, right? So we're saying that the left child, the left part should be root dot right. So this should be on its right. So once you run this, the line of code at line 22, this would look like this. So the 4 now becomes the root, and then the right would be 7, 6, 9. While here we had 2, 1, 3, right? However, now our right should be equal to the left, right? So 2, 1 and 3 should be, so currently since we changed our left to right, we can't access the left that used to be here before, right? 2, 1 and 3. That's why in order to do that we have to store that left of the root in a temporary variable so we can access it later. So it should be root dot left before we actually run this part of code. So now our temporary is equal to 2, 1 and 3. So now our root dot right should just be equal to temporary. Now the root dot right, the right part here, now will be equal to 2, 1 and 3, right? So that's it. So now we were able to swap these two values, right? As you noticed. Now if you look at the example here, now 7 came here, 2 came here. But like over here, we're still not done. It looks like 6, 9, right? So since we're gonna call it recursively, since we call it recursively, it does the same thing for 7 too. So the root now becomes 7, and 9 ends up at here, and 6 ends up here. So our next recursive call would be like that, and then the recursive call for here would bring 3 here and 1 here. So this is a basic logic. It's very easy to implement using recursion. So let me implement it. So I'll just check to make sure there's root, if root, and I will call that, since there's not only left and right, there could be more than left child have children, so that's why we are gonna call it recursively. So how would we do that? In order to do that, we are gonna say if there is a root, so the left would be invert tree, So this would root dot left, and then the right be invert tree root dot right, and we have to say self. Now over here, once we call them, now what we can do is we can say root dot left is equal to the right. Now root dot right is equal to the left. That's it. And we should be good to go. And then we just in case at the end we have to return something, right? We have to return the top, the head, the root, so they get all this as the answer. So we just say return root, and see, as you see that we and it passed. So that's it for the solution. So the reason we called the recursive function again, so it goes deep down. It goes deep down here and starts. So the first thing that gets swapped are 1 and 3. These two get swapped, and then this two get swapped. And then what we do is we say root dot left. So root dot left equals root dot right. So it's gonna swap. Anyway, if you just start going line by line, you will see what's going on in this recursive call. And so that's why I just want to go faster, and then and try solve it iteratively. So how do we use iterative approach? So if you've watched my previous video I made about level order traversal, iteratively doing level order traversal, where you use a queue, right, to do that. So we have we basically have a queue, and we append our root in here. So level order traversal, I'm meaning like going level by level. So first time the root is the first level, so we say val queue, and we pop it. Pop equals q dot pop, and we want to pop it at 0 because q for the since we're using list, the beginning index is a q, is a first line, the beginning of the line. So I would say if popped, then I would say q dot append. If pop dot left, and I would just say pop dot left. Alright, so since we are trying to make the left equal to the right, so alright, now we are going to also check it. So here I'm appending the second level to the queue. So second time we go into the while queue, it's going to go through left and right. So pop dot right, q dot append, and pop dot. To learn more about level order traversal iteratively, go to my other video in this playlist. So finally, what we are going to do, pop dot left is equal to pop dot right, and then pop dot right is equal to pop dot left. Now, do you see a problem here? Since we are saying pop dot left is equal to the right, it's going to overwrite the value of left, and we no longer have access to the previous left, so that's why we have to use temp pop dot left, and then we change that to temporary, and we just return the root, and it should work. So as you see, output was 4729, and there's no any difference. So, and this that works. And so why does it work? All right, now let's take a look. Okay, so first time the queue we start at what? At 4, right? Now we pop the 4 from the queue. The queue is empty now. We pop that. No longer has a root. We pop the 4. Now we said we checked the left side of 4, right? Now the left side is 2, so we appended that into the queue, and we also appended the 7 into the queue. But it doesn't matter. It matters for traversal, but it's not solving our problem, right? Because we want to make a left side equal to the right side. Same way like we did for the recursion. After we push the children into the queue, we are gonna think about solving the problem. This part solves the problem like recursive approach. Like 4 is a root, so when we say pop.left equals to the right, the 7 would go to the left of 4, and then pop.right equals to temporary. It's going to bring 2 to the left. So remember, 2 has its children. So when you just saying pop.right equals to temporary, it's not just going to bring 2, it also brings its children. So 2 doesn't come by itself, it also comes by its children. So remember that. So 7 is going to come by 6 and 9. Now we are done with 4. We no longer get 4 back. However, we change its position of its left and right child. But like at the second loop inside the while queue, our queue is not empty. It has 2 7. Remember, it's a level order, so it's going to go pop 2 now. Once it pops 2, it's going to check if it has a left and right child. So now we popped 2, so we pop 2. We're going to remove 2. Now queue 7 is on the next on the line in the queue, because in the queue it's the line matters. Who came first matters. So 7. Now we append the children of 2, 1 and 3 here. So that's why 1 and 3 gonna wait until 7 is done, because it's a queue. Now before we go into that, now we append the children to the queue. However, the root was 2, right? Now before we forget about 2, we take its left and swap it, right? So like we did here. Now we are at 7, so 9 would go to its right. Okay, what was the left child? Okay, 6 is gonna go to the right of 7, and 9 is gonna come to the left. So we're done. And then we go back again, we pop the 7. Now we do the same thing, we take its children 6 and 9 and put it here. And everything is queue, is waiting, everything waiting on the line, right? Look here. So 1, 3, 6, 9, they're all waiting. So first it's 1 and then next 3. So that's why we use queue to solve that problem. So here 7, and we are at 7 here. And then we do the same thing here. We take its left, store it in temporary, and then 7.left would be equal to its right. So okay, so pop.right, so this would be 3 and this would be 1. So and we do the same exact thing for 1, 3, and so however, these guys don't have left and right child, so it doesn't matter. This part doesn't matter for them because it's none. So it's just swapping the none part. So that's it for the iterative approach, and it's easy to get the hang of it. So we are using a queue, which is extra space. So you are appending every so the queue is, the space complexity would be order of n, while the time complexity would be order of n, because we have to access every single element in the tree. So order of number of elements in the tree. By the way, this problem was asked when Max Howell, he basically, if you remember the software called Homebrew, it's a package manager. He wrote it, and a lot of Google employees use it, I guess. And then he went to interview with them and couldn't invert the binary tree, so he didn't get an offer. That's a little story about the problem. Anyway, so see you guys next video. I can run this so you know it works. Oh, I gotta change this part here. So it should be root. So everything works, and I'll see you guys next video.